Okay, apparently we are live. I'm assuming everyone can hear me on the internet in the future.
Hello, Internet.
Oh, we're not live streaming it.
Oh, right. Anyway, this is my presentation on making video game controllers with Teensy. So we'll start with who am I and why should you listen to me? My name's Tim. I also go by Kiyoshigawa on most of the internet. I do have a degree. Oh no, I don't know how to use presentations. I have a degree in engineering. Apparently presentations weren't a prerequisite. I've been a founding member of way too many hackerspaces in my life. I've self-taught myself a bunch about electronics, PCB design, and programming, but most importantly, I have actually made a bunch of video game controllers with Teensy. And almost all of them work. So, general overview of what I plan to cover tonight. First, I'll go over the types of things you can connect to a Teensy as an input device and how to connect them. Second, I will go over why I choose Teensy, mostly because I'm lazy, but we'll get to that. Followed by general best practices for writing code that will work well as a game controller, cutting down on latency. And lastly, I'll get out all the example code I've written so you can see actually how I do it. All of the example code is also available on GitHub, so if you want to follow along locally, you can find my GitHub account. It's under Kiyoshigawa. I'll just leave that up on screen for a second so you can all take the 2 minutes it will take to spell my name out. Or just ask later, whatever. As I go, please feel free to yell at me with questions or call me out if I say something wrong, because I'm bad at presentations. So, the first most common type of input is the button or switch. So what you're used to seeing on arcade controllers looks like this little plastic circle. Oh, here. But the actual switching happens in a little box down at the bottom that looks like the picture here. So there are usually 3 legs on each switch and a tiny little button. And I'll pass this around for everyone so they can look at a switch if they want to. Actually got a couple in here. I gave you the sharp one. Watch out for the piece of copper sticking out of the bottom. There are tons of different kinds of switches. You've got everything from momentary on switches to fixed, I always forget the word for not momentary. Anybody remember? No.
Transient? Stateful?
I can't think of it. Anyway, lots of types of switches. Keyboard, mechanical switches work. You can even use a banana. That does take a bit of a larger pull-up resistor than the built-in one, so you have to build a slight circuit, but touching bananas will work as a switch in a video game. These ones here that have a wire on them are what they use for the coin counters in arcade machines. So if you put a quarter in, it will fall across that wire, triggering a switch. So as I go through each of the inputs, I'll be showing you a handy diagram that's available on the Teensy website. Every time you buy a Teensy, it comes with a card that displays this. So I give them away like candy at the hackerspace because I own a lot of Teensys and really only need one card. For this first one, I'm just showing the connection for the switch in terms of the whole Teensy, which has a whole lot of pins. You can connect it to any of the digital pins. Those are the gray ones in the diagram. And you just connect the switch one side to ground, the other side to a digital pin. The reason that this works is because of a built-in pull-up resistor inside the Teensy. So for those unfamiliar, a pull-up resistor is tied to the high voltage signal for your microprocessor. And when the switch is open, the circuit is not connected to anything except 3.3 volts through that resistor. So the digital pin will read 3.3 volts. As soon as you close the switch and it touches the ground connection, current can then flow through the resistor and the voltage at that digital input pin drops to 0. So in all my code examples, you'll see when the voltage is low, that means the pin has been pressed, and when the voltage goes high, that means it's been released. Yeah, you can enable the pull-up resistors in software. You can also put a physical resistor in your circuit if you want to use another microcontroller that doesn't have built-in pull-up resistors. I think that's everything I want to say about them. But yeah, with the Teensy, the built-in pull-up works for just about every case except bananas. The other thing you need to know when you're using input switches with a microcontroller is that as you press the switch button down, you think it just goes from not connected to connected instantly, but that's not the case in the physical world, because right as the switch gets really close to connecting, it will electrically switch on and off many hundreds of times very rapidly. So I'm going to open up this website I was linking that shows a pretty graph of that, because he did a better job than I could. So as you can see here, when you push the switch down, it oscillates very quickly up and down when you press and release it. And if you're not careful, your microcontroller can sample fast enough that it will see multiple presses at the time you press the button. So if you, going back to the presentation, you can do what's called hardware debouncing, which involves putting a capacitor in parallel with the switch, and that will stop the physical transitions electrically. I'm not going to get into how it works. The blog that I linked in the slides, which are also posted on the GitHub, goes over it much better than I would be able to now. However, I also use software debouncing, which basically says as soon as you detect that the state of the pin has changed, don't check again for a short amount of time. And I'll get into how the software debouncing works later in the presentation. So that was just a button. Another super common thing that you see are buttons that have lights built into them. So like all the buttons on this controller. Oh, should I point the camera at it? Okay, yeah. Here you go. You can see when you press buttons, you can get lights that turn on inside the button. The way that this works, I'll put this back here, is inside the button there is an LED. I just plug in, kind of hard to see here, but yeah, it plugs into there, and that's slotted up inside the arcade buttons. This is super common, you'll see it. So in addition to the 3 switches, normally open, normally closed, and common, you also have 2 more pins that connect to the LED directly. And I'll pass this around so everyone can look at it. To get the LED out, you kind of twist lock it. So, yeah, and like the slide says, typically they're LEDs now. In the past, there used to be little incandescent bulbs in there. So if you're trying to retrofit an old arcade to work with a new controller, you may need to figure out what voltage the lights were expecting and get that to them.
What's your GitHub again?
GitHub/kiyoshigawa, KIYOSHIGAWA.
Oh, okay. I just got that. Thank you.
Yep. Okay, so there are 2 ways you can deal with the light up buttons. One, you can wire it to a digital pin on your microcontroller so you can control when the light turns on and off with software. And 2 is you can wire it hardwired so that whenever you push the button, it will connect the LED and allow it to light up while you're holding the button down mechanically. So you don't need any additional digital pins or software to control it. So in the first schematic here, you've got the digital pin set up. You just run through a resistor and through the LED to ground. You control it in software by changing the state of the digital pin in your program. In the second one, you run your 3.3 volts through a resistor to the LED to your digital pin, which, as you recall from previously, is connected to 3.3 volts through a pull-up resistor. And then the same circuit applies when you connect the switch to ground. The LED will also be connected and it will light up. And that's how the buttons on the big 2DX controller I was showing you a second ago are wired. So there's no digital pins involved with those. One thing that's very important to take into account when you start getting into lighting on your controllers, if you're only powering this over USB, the most you can get through a typical USB cable is 500 milliamps of current. So if you've got something like 20 white LEDs, you might start overheating the cable or burn out some traces on your Teensy. That can get dangerous. The pins on the Teensy, if you want to control it digitally, are not very good at syncing current. I believe the Teensy LC, I'll get into the variants before, but it only supports 5 milliamps max per pin, which is practically nothing. So that's why I tend to avoid using the direct drive circuit that I showed in this presentation. It makes more sense to put a transistor in there so you can pull more current. If you want to go over 500 milliamps, you need to either use more USB ports or get another power supply entirely. On my big Rainbow 2DX controller, I had to add a whole 12 volt power supply to run all the lighting effects that's completely separate from the Teensy. Yeah, so that covers buttons with lights. Onward to the venerable joystick. I'm sure many people remember playing, camera, venerable joystick. People remember playing video games that had the 8-way joystick, like old Street Fighter, Mortal Kombat arcades. The way this works is actually there are 4 switches on the bottom, and there's a stick that sticks through the joystick that presses the buttons underneath. So to get up left, you just move the stick to that position and it presses the 2 limit switches. So really, it's the same circuit I've already shown you. There's nothing too special about it. It's just 4 buttons instead of 1. You can pass that around and see how it works. There are many types of it, but the principle is generally the same for all the digital 8-way joysticks. The next kind of input device I will cover are analog inputs. There are lots of ways to get analog inputs. You most commonly see them in joysticks. So the analog sticks on your favorite console controllers are actually just 2 potentiometers in an XY. You can kind of see it in this picture here. I don't have any disassembled, but you're basically moving 1 pot in the vertical direction and 1 in the horizontal direction to give you the full range of motion. Joysticks are a collection of many analog inputs and buttons all built together. We'll go over this particular joystick in a bit more detail later because we retrofit one to work with the Teensy. You can also have sliders or pretty much any other kind of input signal that isn't just on or off but gives you a range of voltages can be turned into an analog video game input. So the way these typically work is with a simple voltage divider potentiometer circuit. So what you've got inside, I don't really have anything great to show visually for this, so I'll just try to explain it, is you've got your high voltage on one side and your ground on another side of a resistor, and then there's a wiper that adds a connection partway through the total resistance. So if you're right in the middle, half your resistance is on the left, half your resistance is on the right, and you'll measure half the voltage. If you're 3/4 of the way over, you'll measure 3/4 of the voltage. One thing that's important when you're making video game controllers is to get a potentiometer that has a linear taper, not a logarithmic taper. So all the potentiometers used for like audio volume control have a logarithmic resistance value, so it doesn't evenly increase the resistance as you move the wiper. It goes up by powers of 10, and that will not give you very good results in most video games when you're trying to accurately position a joystick. So keep an eye out for linear potentiometers when you're doing that. On the Teensy, everything runs at 3.3 volts, so your voltage output needs to go from 0 to 3.3. If you've got something like a load cell with a circuit that's outputting from 0 to 5 volts, you'll need to somehow modify that to get it within the 0 to 3.3 volt range, or you risk damaging the pins on the Teensy. You can also use microphones as an analog input. It varies in quality. Like the old original Nintendo DS had a microphone input that was basically, if you're not screaming at it, it won't register anything, and that's all just due to the way they set up the circuitry that's supporting it. So I'm not going to cover how to hook up load cells or microphones too much, but potentiometers, the circuitry at least, is very simple. The software does most of the work. So, yep, here are some pictures for how we rewired an analog joystick, which is sitting on the table right here. Wave it at the camera for, oh, I'm stuck on a microphone. And a backpack. All right, so here's an analog joystick. This used to have a 25-pin game port connector on it. We removed the old circuit board that you can see here. It used to take the potentiometers with only 2 pins, so the rest of the voltage divider circuit was built into the computer for the old game ports. And what we did is we took a Teensy and we connected all 8 of the buttons to there, and then we connected 3.3 volts to one side of each of the pots. We connected ground to the other side of each of the pots, and the middle pin on the pots we connected to the analog inputs on the Teensy. And those are these orange pins here that say A0 through A12. Note that A10 and 11 are shown on the back of the card, but not in the picture. So you can have up to 12 analog inputs on a Teensy at any point. Anyway, I'm getting sidetracked. Once we connected the simple voltage divider, it was all just down to software to turn this old joystick into a functional USB joystick instead of a nightmarish analog joystick. What just happened to my screen? I apparently set this on the controller that I have macroed to launch a video game. So just a moment and it will let me close that. Okay. Sorry about that. The next device I want to cover are encoders, which is how I made the disk controllers for this controller here work. I'll let John. So as you can see here, I have a disk controller, spins around. This is using a digital rotary encoder. And the way that the rotary encoder works, I'm actually going to skip ahead to this slide and then go back to connections in a second, is that it shines a light through 2 panels that are spaced apart with photodiodes on the other side. And they're offset such that as it rotates, the first light will turn on and then the second light will turn on. And then the first light will turn off and the second light will turn off. So as it goes through that, you can tell which direction it's going, and by knowing how many of these transitions are in the full circle of the encoder, you can know how far it has gone and in what direction.
Yeah, I was going to say, and in what direction is the next one? So,
Okay, so
because it seems like it's just if both of them are on, essentially.
Yep, I have actually prepared a thing that shows me spinning it one direction and then back the other way. So I hooked this up to my logic analyzer and recorded the inputs from the encoder directly. So let me square that off. This will probably be hard to see on the YouTube video, but as you can see here, it's saying channel 1 is turning on before channel 0. So you go 1, 0, 1, 0, 1, 0, all the way down to here. And then when I stopped, you can see the frequency slowed down. And as I started spinning it the other direction, now you can see channel 0 turns on first, and then channel 1, 0, 1, 0, 1, 0, 1.
Okay, so it's not which channel turns on
Right.
first.
So you
Fine,
measure
fine.
1, 2, 1, 2, or 2, 1, 2, 1, you know the direction it's going. When you get to the code sample in the library, there's actually a neat table that they wrote that basically says if the state is this and it changes to this, that means it's traveled one step in that direction. And they've got a whole lookup table that they use. I'll cover that in just a moment. Now we are back to the slide. So when it comes to connecting the encoder, they'll typically have 4 wires. The one I have has 5, but one is a shield that's tied to ground. So the 3.3 volts is obviously your voltage source. Ground is ground. That powers the light that's shining through them. And then on the outputs, you need to include your own pull-up resistors. For some reason, it did not like the ones in the Teensy. I believe the reason on the case of this particular encoder I bought from Amazon is that it runs at 5 volts, and the 3.3 volt pull-ups were not high enough voltage for it to operate correctly. So that's why I put in my own 10K pull-up resistors to 5 volts. So my circuit's actually 5, not 3.3. But if you get an encoder that operates at 3.3 volts, then you don't need to worry, and you can use the built-in pull-up resistors on the Teensy.
Did you have to step down the voltage after that?
I did, and there's a really, really ugly voltage divider circuit over here that's using 6 resistors because I did not have resistors that worked out evenly to a good value. But it's working for the demo, so that's all that matters. In reality, your circuit should look about like this one. If you need to use 5 volts, just find a way to step down the logic signals before you connect them to a Teensy LC. The Teensy 3.2, 3.1, 3.5, 3.6, they're all 5 volt tolerant inputs, so you don't even need to step them down. You can just connect to the pins directly. Let's see, yeah, powered. Okay, and I covered the basics of quadrature encoding. This is just from Wikipedia. There's a whole paragraph telling you what I just told you. So the next kind of input device I want to cover is something that probably doesn't come up all the time, but it's a handy way to get a bunch of inputs hooked into a microcontroller. Because MIDI device control boards basically are a bunch of input knobs already wired together that send their data constantly. So one use for it would be if you were making a Rock Band game, you could use your MIDI drum set and just interpret the signals and send key presses or joystick button presses to the game directly. As far as the connection for MIDI, MIDI is a really old protocol. It is actually just running standard RS-232 serial at a weird baud rate of 31250. So it's super easy for a microcontroller to interpret. There are hardware registers built into it that do all the heavy lifting for you. The hardest part for the Teensy is you need to step it down from 5 volts to 3.3, and the correct way to do that, according to the MIDI specification, is to feed it through an opto-isolator or a transistor, just to prevent you burning out your pins. Luckily, you can get breakout boards, which is what I have. Here, I can show you on my desk. The camera's running really slow. You can see right there in the middle is actually a MIDI breakout board that has built this circuit for me. I got it on Amazon for about $10. So if you have a big MIDI controller with 200 pads and 30 knobs on it, you can turn any of those into computer USB inputs using a breakout board like this. What have I missed? Yep, that's about it. And then I've just thrown together an other category. There are basically anything you can hook up to a microcontroller, you can turn into a video game input if you are so inclined. One of the most useful ones I've found is any Nintendo Wii peripheral that plugs into the bottom of a Wiimote is actually running the I2C communication protocol that's built into Arduino and Teensy microcontrollers, and pretty much any modern microcontroller will have a way to use this protocol. So these are already fully functional game controllers, and people have written libraries for it. All you have to do is plug it in and say, when you see this button, press do something. So if you really just want to use a controller you already have, you can plug it in, and it's super easy to do. There are other things you can get. Accelerometers will generally output digital information to a microcontroller over various protocols. I've seen them serial, I've seen I2C, I've seen SPI. However you get the information, you can then interpret it and use it as joystick axes or whatever kind of output you feel like. I've seen people use temperature sensors if you want to like recreate one of those how hot is your love arcade games where you just hold the stick and it measures your body heat and gives you a rating. You can do that with a temperature sensor. You can also use touch screens as an input. There's a whole lot of back-end software, so I won't get into it. This is a picture of a rhythm game called, Dance Maniacs, and it uses IR light sensors to tell when you wave your hand above or below something, and that registers as a button press in the video game. So, now on to the Teensy. Why am I using the Teensy and not something else? I'll start with what Teensy is. So the Teensy is an Arduino compatible microcontroller brand made by a company called PJRC. A guy named Paul Stoffrigren or something like that, I have no idea how to pronounce his last name, makes these boards. He's basically a hobbyist who does this out of a spare bedroom in his house. This is his website where you can see all the boards laid out. You can actually buy them directly from him through Amazon. So essentially, he has made an Arduino compatible circuit board that runs on ARM processors, which are faster than the Atmel boards that Arduinos typically run on. And they have built-in USB controllers, which allows you to use the libraries he provides, free and open source, to turn your Teensy into several different kinds of inputs directly on any computer. So once you've got this programmed, you can take it, plug it into any computer, and it will show up as a generic HID compliant joystick, keyboard, mouse, flight sim, or MIDI device. And again, these libraries are all freely available on his website. He's got them on GitHub. Where is it? Code library shows. I'll be getting into all of these more in a minute, but this is the... Yeah, so the reason I like Teensy is because Paul Stoffrigren has done all of the work for me. You can just tell it this will now be a USB joystick / keyboard, hit upload, all the libraries are built in with the software, and it's a walk in the park to start playing video games once you've connected your inputs. So, the way Teensy works is you start off by downloading the Arduino IDE. It's an open source program for programming Arduino microcontrollers. It comes in this ugly blue color, and once you've used it for a while, you will start using a different IDE, and it's basically a glorified upload button. The next step is you go to the Teensy website, and for Macintosh, Linux, or Windows, you can just download an installer program that adds the Teensy bootloader to the Arduino IDE. It installs a little program here and integrates all the Teensy boards into the Arduino IDE. So you can select your board is, in this case, a Teensy LC. You can tell it here, I want this one to be a keyboard, mouse, or joystick. I want this to just be a keyboard. I want serial keyboard, mouse, or joystick, etc., etc. So he's done all the heavy lifting. He pre-programs the board. His software comes with all the drivers you need on any operating system. And in general, once you've installed it on the board, your operating system already has generic HID input drivers, so you shouldn't even need drivers beyond programming. Where am I going with this? And then, yeah, so that's the Teensy Duino software is what it's called. and these links are in the slides, which are on the GitHub, so you can find them easily later. Now I'll go over the libraries and some of their capabilities and limitations. So the first one I want to cover is the keyboard library, and basically it follows the standard USB keyboard driver, which gives it the full functionality of any keyboard, including media keys. However, that standard library only supports a 6-key rollover, which means you can't press more than 6 keys at a time before it starts losing extra button presses. So, for example, my 2DX deck that has 28 keys and 2 discs would not function well as an emulated keyboard because you have to hit too many buttons at once. It is easy to customize the code, so you can press multiple keys, or you can set up long key macros as a function that you can call. So if you want someone to do the ultimate combo in a fighting game at the press of one button, that's just simple programming the order of button presses. It can also be helpful if you're trying to take a more modern controller and use it with an older video game that doesn't let you map keys to whatever you want. So you can make a controller that's custom fit and tell it, even though I'm pressing the W key, it's now a Q for the purpose of this game. The next most pleasant library from them is the Joystick library. Oh, wait, I wanted to go back here. Sorry, before I go to Joystick, I want to go back to the keyboard library. They've got tons of super useful documentation on their website. The easiest way to use it is the press command, which basically pushes the button and then releases it immediately after. And you just say print, sorry. So it works just like the Arduino standard print command. So you can write like you're typing a whole message out, and it will send that whole message as individual key presses in order. The other way you can use it is to press and release keys directly, one at a time. So if you want to hold down buttons, you need to use the press and release syntax instead of the print syntax. And there's also on their website a table that shows you all the hard-coded defines for key names when you're using those press and release buttons. So if you want to know how to hit the rewind media key, you have to look on this table to know what to type into that function. You can also micromanage it a bit further because it allows you to use modifier keys in addition to those 6 rollover keys. So you can actually get up to, it says in here somewhere, it's either 10 or 12 actual keys pressed at the same time, but 4 of them have to be modifiers for it to work, which gets kind of hacky and probably isn't the best idea if you're trying to make a reliable game controller, but I want people to be aware that it exists. So now I will move on to the Joystick library. Sorry, I jumped the gun a minute ago. That emulates the full functionality of a standard HID joystick, and that standard joystick comes with 6 axes, so you've got your X, Y, and Z rotation typically, and then you've got a throttle and 2 other analog axes that are standard supported. It also supports 32 buttons at a time and a single 8-way hat switch on the standard HID driver. This library, I'll get into it in a second, allows you to precisely control when your button presses are sent. The default is just as soon as you push a button, it will send that information over USB, but you can actually have it wait until certain conditions are met and send everything at once if you want to. And this also has the benefit that you don't have the 6-key rollover limitation. If you want to push all 32 buttons while moving the axis at the same time, that is entirely possible with the HID joystick. So here is their website on this. It shows you generally where the axes are on typical types of controllers. So the way to send information is the button function. You send it a numbered button, and then 1 means it's on and 0 means it's off. You also, whenever you're setting up a joystick, if you want to center the joysticks to a default value so they're not constantly sending commands to a program, you need to manually do that in your setup function, because otherwise they all default to 0. And in a bunch of games, if you have extra buttons you want for it, but you forget to reset the joysticks, it may interpret that as your X being all the way to the right. So your spaceship will be spinning around and you won't know why. And it's because you didn't reset the value to a default at the beginning. Yeah, that pretty much covers the joystick library. Oh, except for if you wanted to do the feature I described earlier where you manually control when the most recent button presses are sent over the USB bus, you have to turn on the use manual send function and then add a send now command to your code that tells it precisely when to send. I haven't really had any need to do that, but it is possible. So now you know. The next library I want to cover is the mouse library. I have used this almost never, but it does exist. Depending on your operating system, it has different features. You've always got the ability to move a mouse and click your standard left, right, and middle click. If you set it up right, I'll get into it on PJRC's site here. Let's see, they've got a whole, so you have to set up your screen size, and this only works on the ARM-based chips. It doesn't work on the older Teensy 2s that use Atmel chips. You can move the mouse to a specific position on your screen, but it's pretty buggy and it doesn't always work, so be careful messing with it. It may not be everything you want it to. Again, I haven't done a ton of games where I needed a mouse input through Teensy, so I don't have a whole lot of experience with that, but it is available. And the screen position direct movement to a specific location doesn't work on, I think Linux doesn't support it natively, and people have had mixed luck on Macs. The next one, there is a Teensy MIDI library that allows you to turn any Teensy into a USB MIDI device. So you can take these inputs and send MIDI signals to your computer and use it for any kind of music programming program that takes MIDI as an input. So if you want to make your own MIDI controller board with all the knobs and buttons like the ones you see, you can do that and send MIDI signals over USB to your computer. And I capitalize the I in with. Unfortunately, the way the default Teensy libraries are set up, you can't run MIDI at the same time you're also using a joystick over the USB port. I'm not sure why, because it supports serial at the same time you're using the joystick, keyboard, and mouse. So I'm thinking there's a way to do it in software, but I haven't messed around enough to figure it out. And I'm already rambling too much, so I'm not going to get too deep into that during the class here. But yeah, you can use all this game input knowledge to make your own MIDI controllers is the gist of that. They also have this crazy flight sim library. So if anyone's really into flight simulator games that have an interface, I believe the popular one everybody talks about is X-Plane. It outputs information from the game to the microcontroller, so you can set up displays in the real world that will show you information from inside the games. And yeah, again, I haven't done any of this because I don't have flight simulators that use this technology yet, but it is available and the library is built in with Teensy, so all you have to do is configure it properly. And they've got a whole page about how to do that, but again, outside the scope of this class, other than letting you know it exists. So I will move on to part 3, which is how to write code that is going to be responsive when you're trying to game, because the last thing you want is to push a button and have it wait half a second before it registers in your game. So the way to do this is to use state-based programming. You don't want any delay functions in your code except in very specific circumstances, which I'll go over. So for those, I'll just go over in general how the Arduino programming environment is set up. It runs on a microcontroller, and it does a bunch of internal setup before you can do anything. And then it calls a setup function, which will run one time as your controller is reset or turned on. And after that setup function, it calls a loop function, which is set inside a while one loop. So it will just run through all the code in your loop, jump back to the top, and run again and again forever. So the first example everyone sees when they're programming Arduino, you go to File, Examples, Basics, and pull up Blink. And I know this is impossible to read, but you can see here you define a pin number, it's LED 13. You go into your setup function and you say that pin is an output. And then the way it's written is you turn the LED on and you delay for 1000 milliseconds. And then you turn the LED off and you delay for 1000 milliseconds again. And the reason this is not good code for a game controller is that if you were checking inputs to see when the button changed, during that delay, it would not check anything. It would just sit there. The way delay is written on a microcontroller is it just sends do nothing to the processor over and over again until that much time has passed.
So those are essentially knobs, right?
Yeah, it's just no ops over and over again for an entire second, and then it will continue your code. So the way around this is another example that most people don't seem to notice called blink without delay. And this uses state-based programming. So you still declare your pin as this, but now you write state variables up at the top that says the state is low. The last time the LED was updated was 0 milliseconds ago. The interval you want to wait before the LED is updated is 1000 milliseconds. So the setup still works the same. You have to say the pin's an output. But then when you get down to here, you say the current time is this many milliseconds. And then you check if the current time minus the last time the LED was updated has longer than the interval that you want, then you can do your update code. So instead of saying, I want you to be high, and then wait a second, and then I want you to be low, it says, has a second passed? Okay, now I'll do something. So if this condition isn't true, it skips the update part, and your code keeps going. You'll note there's no else on here. It doesn't do anything if it hasn't been a second yet. So it just says, has it been long enough for me to do something else? And then it can do that. So if you had other code in here that was checking your button inputs to see if they'd changed, it's not feeding the processor do nothing for an entire second before it can check to see if something's changed. It just skips over that part of the code until it's ready. So I'll kill those because it's already confusing enough. And pop back in here. So state-based programming basically means avoid delays. And I have a ton of examples of the actual code that all these game controllers are running, which is the last part of the class to go over. So the basic structure for the controller is before you even get to the setup function, you need to declare all your constants and variables that you're going to need down there throughout the program. This is where to make things like debounce objects in software, which I promised I would cover later, and I still will. You can set up hardware MIDI controllers on there, so that's to use the Amazon one to read the inputs over serial. The I2C Wii devices that plug in, they also need to be set up before your setup function. You basically have to say, I have one of these objects, and the libraries that are included or free online do all the heavy lifting for you, but you need to know to set them up before you try to use them. Then inside the setup function, you need to set your pin modes if your libraries haven't done it already. Yeah, so that's turning on your pull-up resistors, so you know, like if you have a switch, you need to turn on the pull-up resistor in the setup, or it won't operate correctly because the pin will be dangling in the ether, essentially. Then you also need to run any initializations that are required by the libraries you set up before, and I'll go over specific examples of that in a minute. The last part is the loop, and inside the loop you need to do three things essentially. You've got to update all your inputs so you know what state they're in. Based on that information, you then need to send that information over the USB libraries built into Teensy to your computer. I said three things, it was really only two. Sorry. So some objects, like the bounce object, which I'll cover in a second, already have state variables built in, and you just have to call the update function for that library. Others, like analog inputs, you're just manually doing an analog read on that pin to see what the current voltage level is for that input. Either way, you just call an update function, and based on the information you get during that update, you then send the information out as a key press, a mouse movement, a joystick button press, whatever you have. Again, you want this to be totally non-blocking code. If you start putting delays in there for any reason, that just means the processor can't keep checking your inputs and will wait that entire time before doing so. So, I have now made a whole lot of generic code examples that I will go over. Again, there's a link to my GitHub. The game controller code examples repo is the one that has all these slides as well as all the code examples I'm about to go over here. Yeah, so I'm guessing everyone's already on the GitHub if they want to be. Do I need to leave the link up for anyone to write down if they're still after it, or are we good? Okay, moving on. So the first code example I'm going to do is called single button. And basically, the library I'm going to use is that software debounce library I've promised to explain, and that's what I'm going to do. You'll also find in most of my code I have a debug variable defined at the top. And what this does is it allows me to turn off serial output if I don't need it anymore. So I'll cover that when we get to my first debug statement down the road. So as I mentioned before I even get down to the setup here, I start by defining some variables. So the first one I define is a serial wait timeout, which I use in the debug. When you first plug in a microcontroller, it takes it a second for the serial connection to establish with the computer over USB. I put that in there so that if the serial connection doesn't get established, it will move on in 10 seconds. If you don't check for the timeout, your serial may not establish correctly before it gets to the loop. Or you could be stuck waiting forever for serial to connect, even though it never will, and you'll never get to the functioning controller. On to the next variable I call bounce time. This basically says as soon as you detect that the state of the button has changed state, don't check again for that many milliseconds. So I typically set this as low as I can get away with without seeing double key presses show up when I push a button. 3 to 5 milliseconds usually works if you've got nice buttons. In the case of this guitar controller, which I made out of an old Wii guitar controller. Oh, sorry, camera. These switches are old.
You're sending character turns
Am
to
I?
your editor.
Nice. Well, it's working. Thank you, Parker. Anyway, these switches are old and sad, so I actually had to up the debounce time to about 20 milliseconds on here, which impacts its ability to play. So I need to either replace those switches or clean them or do something, because
Use the hardware you showed us earlier, maybe?
maybe I can try it. I didn't have time before the presentation, but yeah, if you've got particularly crusty switches that are sloppy, you may need longer debounce times. Depending on your application, 20 milliseconds may not matter. Like 15 milliseconds is about the most people can perceive in reality. So if you're faster than 10 to 15 milliseconds, that's like 60 FPS. Yeah, 15 milliseconds is 60 FPS. 7 milliseconds is 144 FPS. So if you can keep your refresh rates below that, then you're as fast as any game you're going to be playing, frame for frame. Anyway, yeah, then like the previous example, I declare which pin the input is on as the button pin. And so I just found out while making this presentation that the bounce library I'm using has been deprecated, and now there is a bounce 2 library that everyone has switched to. So I'm just going to ignore that that's happened, but apparently it functions essentially the same way. They've just cleaned up the syntax and given it more neat features. Anyway, the way the library I have set up is for each input you want to debounce, you declare a bounce object. So in my case, I'm declaring button is on the button pin, and the bounce time that I defined up above is how long it will wait before checking to see if it's changed state again. So in the case of a single button, that's all you need to do before the setup. So then in my setup here, I've got a serial begin statement, and this here says if serial hasn't been connected, wait. So it doesn't do anything except check to see if more than my wait timeouts happened and it breaks. You'll see that at the top of most of my code. That's just how you set up serial so it won't fail and stop your controller if it's not connected later. Then here I've got my if defined debug. I'll print out this is the key press testing. The next thing I do is I set the pin mode as an input with a pull-up. So you've got to say input underscore pull-up if you want to use the pull-up resistor. You can't just call it an input. If it just says input, then the pull-up resistor is not connected and you won't get consistent values. You'll either always be low or it'll be floating, and you could get gibberish when it's open, and it'll always be grounded when it's closed. Neither case is good, so make sure when you're using buttons, always input pull-up. This is the part I warned you about where you have to set your joystick axes to center if you want them to default to the center. Otherwise, they're all the way to the right, and your spaceship will be spinning and you won't know why. Ask me how I know. Okay, so my loop function is extremely simple. You just call the update buttons function. And that update buttons function says, so remember, button is a bounce object, and it has a built-in function called update. So you check that for each button. If the button has changed state, so if it goes from low to high or high to low, update will return true. Then you can check which of those two options happened by saying, was it a rising edge, another built-in function of the bounce object, or a falling edge? So in the event that it's a rising edge, that means it went from low, which is connected, to high, which is released. That means I want to let go of the joystick. If you remember back from the Teensy web page, you say joystick button number 1. When it is released, you set it to 0. And then I print a message released if debug is on. Otherwise, if the update was true and it's a falling edge, I want joystick button 1 to be pressed down because it went from high, which is the disconnected state, to low, which is the connected state. So that's the most in-depth I'll get on buttons for the rest of the time. I'm now going to actually disconnect all the rainbows so that I only have one Teensy plugged into my computer. And then, so yeah, I will now upload the code. So you make sure Teensy LC is selected, because that's the controller I'm using. I want it to be a serial keyboard, mouse, and joystick. The CPU speed is 48 megahertz. The keyboard layout for the USB keyboard connected to your computer is US English. You can set it to whatever you want if you want to use different languages. Optimize, I always leave on smallest code. It takes a bit longer to compile, but it's not a big deal. And then the serial port is the port your Teensy is currently connected to. Since I've unplugged all the other ones, I only have one, which makes it easy. So now when you hit upload, it will take half an hour to compile on this laptop. And when it's done compiling, it will pop up a little program that looks like this if it wasn't already open, which is actually taking the compiled file and uploading it to the Teensy over USB. One thing to know about, oh, it got angry. No Teensy boards were found. What is plugged into this port? Just a second. Let me find the right cord. It should be. Nope, that is the USB camera. Sorry. Okay, we'll try that again. Port. Oh yeah, see now it actually shows up that it's recognized it as a Teensy on COM7. So when I hit upload this time, it should compile faster since it's compiled once. And yeah, so that's the good message. And it uploaded through this program, which is installed with the Teensy Arduino. So now that program should be running on my Teensy. And as you can see, it shows my code of key press testing and released. Now I'm also going to pull up this video on the other screen. I know I'm getting about 1 frame per second on the camera because this laptop can't handle the high definition stream, but as I press the button, you can see it says pressed, and then I release and it says released. And you can also see that I'm not getting any double presses either, which is a good thing. If you see pressed twice in a row, it means you probably need to increase your bounce time. So that is the first example of one button. Multiple buttons. The code is basically the same, so you still need the bounce library. I still define my debug, serial, bounce times, but what I do differently now is I say I have more than one button. I have 3 buttons. And instead of saying button 1, number 2, button 2, number 3, etc., I just define an array that calls out all the pins that the buttons are connected to. If I want to add more buttons and connect them to more pins, I can just increase this up here and increase this array to include the more buttons. The bounce library, bounce2, I believe will let you declare an object once and attach multiple pins to it. The bounce library I'm using in all my examples makes me declare each one as a separate bounce object. So instead of calling my bounce object button this time, I've got B1, B2, and B3. And then to make my life easier for the rest of the code, I make an array that contains all my button bounce objects. That way I can iterate through it later and I don't have to type out everything manually. Again, my setup is pretty much the same. But instead of saying pin mode B1 is input pull-up, I say for every button in my button array, declare it an input pull-up and print out a debug message. Again, the joystick centering code. And then my loop is still update buttons. However, this time instead of checking, so this code is pretty much identical to what we just went over. But I put it in a for loop, so it will iterate through the whole button array and check all the buttons at once. So now I will upload that, the multi-button, and I shouldn't need to change, yeah, it's still set up with the same settings as before, at least in theory. and we wait for uploads, I'm going to drink some water because my throat is getting scratchy. And it's mad at me because I left the serial monitor open. It can't use the serial port to upload code if I'm monitoring it. Okay, and it says done uploading, so nope. I've done something horribly wrong. Let's see, what have I done? Yeah, that's... Okay, we'll try one more time. Okay. There we go. So now I can make this... Oh, I have to scale up this one in order for that to be readable. Then I will reset the Teensy. Okay, so here, and I'll pull up the video again, you can see I've got 3 mechanical keyboard switches that I just put in there. I can press 1, 2, and 3 and release them in order, or I can hold 2 and press 1. And as you can see, it is keeping track of all of them and responding as fast as it can spit out serial data to you. So that's how I set up multiple buttons. On to the next example, after I remember to close this. So we're going on now to analog inputs. And this was giving me trouble before the class, so I'm going to disable serial output on this demo and just show you in the joystick interface. I don't know why it's happening, and I won't get into it. Anyway, I've got the same serial wait timeout setup you saw before, and then I have a number up here, because if you just read directly off the analog pin, it tends to jitter a little bit, because it's an analog physical device, and the resistance isn't perfectly stable, and the readings aren't perfectly stable, so the voltage may shift slightly, and that'll give you jitter in your readings. So what I do is I average the last 20 readings that we've gotten and output that value instead of just the direct read value. Default joystick value, instead of typing in manually, I just made it a global variable. And the pin numbers on the card show up as orange, and they are a defined term, so you can call it out as A0. You don't need to say pin 14. That makes it easier to read and comprehend, in my opinion. I also have an index variable for keeping track of which of the 20 readings we're currently on, so I don't overwrite the same reading over and over again or anything like that. I also have an array that stores all 20 readings, so I'm only updating one of those 20 readings every cycle. And it just keeps the last 20 in there and starts over at the beginning. Again, I've got my standard serial beginning. When you set up an analog pin, you do not want that pull-up resistor on because that affects the resistance of your circuit. So you just want to declare it as only an input. Again, this is your standard center your joystick values by default. Then I also fill in the analog reading array with the default value so that you don't start out with a bunch of zeros and it slowly ramps up as soon as you turn it on. The loop looks pretty similar to the button loop, where I have a function to update the analog like I did update buttons, and then I have a separate function in this case to set the output for your joysticks. The update analog basically says the current analog reading is the analog read from the pin. That's the function built into the Arduino libraries that takes your voltage reading at the pin and stores it as a 10-bit integer from 0 to 1024. The analog, and then I set the current the current location in the analog reading array to the current reading. After I've set that, I increment the location that will be set by 1, and then if it is more than the number of readings, it resets to 0. Then once I've got the reading, I update the output to the joystick, which shows up as the, sorry, what am I doing? So what I do is I basically add up all the numbers in the average array and divide by the number of numbers in the average array to get the average value, and then I just set that value to the x-axis on the joystick. So I will now upload this code to the thing, and you can see it working. I don't know why I have to do this, but I do. Yeah, disabling serial made it work earlier. Hopefully it works now. And again, compiling it for the first time takes a long time, and then after that it's much faster. One other Teensy board found. Okay. Sorry for the boring upload delays.
It's back to life. Compile time.
Okay. So it says it was successfully updated. As you can see, I have a keyboard/mouse/joystick HID object that shows up on the computer. If you open the properties window, you can see all the various axes here are set to the middle, except for one, which I'm gonna put this over here, pull up the video. If I move this potentiometer that I have wired onto the board, nothing is happening. Why? Because I have to be selected in the window. But yeah, there you go. You can see that as I move the potentiometer, the x-axis is being updated. And even with 20 samples being averaged together, it still responds very quickly to my actual movements. Depending on the processor you're using, the analog read time, it's generally in the order of like 30 to 50 microseconds per analog reading. So be aware that it takes a lot longer than a button, which is 50 cycles at 48 megahertz, which is less than a microsecond. So if you've got 30 analog inputs, you may start to see some delay because it takes so long to read all of them. Also, I don't know how you did that because there are only 13 analog input pins on the Teensy. Good work. Okay, on to my next one is the quadrature encoder I showed you before. And that one, there is a new library to include that is not the bounce library called Encoder.h. That's also included with the Teensy when you install it. It uses hardware interrupt pins on the Teensy if they are available. And what that basically says is as soon as the state of that pin changes from low to high or high to low, it will immediately call a function taking you out of whatever code you're running and update the position of that encoder. So it should be capable of keeping track of itself even when you're doing something else. So you don't have to worry about being in the middle of another function when you're rotating it and it won't get it. I declare some variables here that just make reading my code easier, like positive, stop, negative, left, and right. Instead of seeing a bunch of numbers that don't mean anything, you can see what I intended them to mean. I also define a variable called the move timeout. So the way I have the encoder set up is if you aren't moving it, so its position value isn't changing, it will stop sending a signal after the move timeout, which in this case is 100 milliseconds. I've also got defined down here a step threshold, which is unless it moves 20 position increments, it won't consider that as having moved at all.
What's kind of a real world value of how many steps would be in a full rotation?
It depends on the encoder you buy. So the encoder I have for this demonstration has what they call 600 pips per revolution.
Okay.
And it actually reads 4 times that because you've got the track 1 on, track 2 on, track 1 off, track 2 off. So 4 times 600 is 2,400. So I have 2,400 steps every time this goes around the circle.
Okay.
And if you have like a simple one like on your car radio, that may only have 10 to 20 pips per revolution.
Really?
So you move it's still only a 20th of a circle, so it doesn't feel like a lot, but you would not want a step threshold of 20 because you'd have to move it all the way around once before it would even register. So you can fiddle with these variables depending on the encoder you buy. The encoder is connected to 2 pins, as you saw, an hour ago at the start of the presentation, one for each track signal. Those are just pin numbers. You can set them to whichever digital pins you connected it to. And then you declare the encoder object. I named mine knob, and just tell it which pins it's on. One thing that had me hung up for a while is do not declare the input pins in your setup with the encoder library. It does that inside the encoder library, and it checks based on hardware what will actually work. So if you try to do it yourself, it overrides the hardware closer to the base register settings and makes nothing work at all. And I spent like an hour banging my head against the disk because I couldn't figure out why that was happening. So don't declare your encoder as an input or an output pin. It will do it for you with the library. I've also got a bunch of global state variables that I'll cover as you see them. These are just default values. So the setup looks about the same. There was a part in here where I declared the variables as inputs, but that was a terrible idea. Just don't do it with encoders. My loop looks pretty much like the other loops you've seen. I've got an update encoders function, and then I have a function that sends information out on a, I believe in this case, keyboard, based on what the encoder does. So my update encoders function is I want to get a position reading from the encoder. And the encoder library is always tracking its position through interrupts in the background. So I just have to call this function and it will say, currently I am this many steps positive or negative from the origin. Then if my new position is greater in the left direction or the positive direction compared to the threshold that I have from its previous position, I will tell it that the encoder is now moving in a positive direction and it last moved at the current time and it is not stopped. And then I have a debug print function here that you'll all see on serial in a second. The same thing is true if the position is going down by more than my threshold. I call it out as showing it is now moving in the negative direction. It last moved at the current time and it is not stopped. And then I print the debug position. If it has not moved enough to trigger either way, then I will say, if it's moved more than the timeout time, then I will say the encoder direction has stopped. So it will know.
It's not moving.
Yeah, when it is no longer moving, it sets the encoder direction to stopped. I also, so this is never ever going to happen in the real world, but in the event that the encoder is about to overflow a 32-bit integer signed, I will write its position back to 0 so that doesn't happen. And there may be a very slight hiccup if you've been spinning the encoder in one direction for about a day. But in the real world, this shouldn't happen. I'm just paranoid. So now you see my key press. Since I went to all the trouble of saying the encoder direction is positive, then I can tell it, so I do have this set up as a joystick. So essentially I've got the encoder set up as 2 buttons. If it's going one direction, you press up. If it's going the other direction, you press down on the joystick. So button 1 is up, button 2 is down. What happens here if you're going in the positive direction is it will press up and release down. What happens if you're going in the negative direction is it will release up and press down. And then if it's stopped, it releases both up and down. So if you go straight from negative to positive without getting to stopped in the middle, it will still turn off the other direction. It can't go up and down at the same time. And that's why this is written the way it is, and the rest is just serial debug. You can look into it if you want. So now I will embiggen this and attempt to upload to the encoder code. We'll pull VLC up. I'm going to drag the encoder into the camera. It'll probably catch up about the time the compiling's done. Still compiling. Okay, and open the serial monitor. Okay, so you can see here it says encoder test. Since I haven't moved it, it's not reading any movement. If I turn it one way, the position number will increase, and then if I stop for 1/10 of a second, it says it stopped. If I turn it the other way, the numbers get negative, and it says it stopped. And I can go forward, backward. And because I've set a threshold for how much it can move, you'll notice it's jumping up at least 20 at a time before it registers anything. You'll also notice that one turn adds almost 3,000 pips, and the Teensy's got no problem keeping up with all the pips per revolution. I've actually found on my big 2DX controller that I can lose pips if I'm going too fast, just because it'll send 2 before the interrupt function can even finish running. So I probably should have used lower resolution encoders for this project, because it's way overkill for what I'm doing. Oh well, live and learn. Moving on.
Well, for your 2DX controller, it doesn't matter how far, you're not doing anything precision, just
Right,
sending it.
it's just lighting effects that are tied to the position, so I had to just fudge the numbers until it looked good instead of actually being able to accurately track exactly where the disk was and keep the lighting tied to it. So the next one I want to cover is how to use the hardware MIDI library. So I mentioned the USB MIDI library earlier, but there's also hardware serial pins built into the Teensy. They show up on the card as, what color are they? They are the light purple. They'll show up as RX1 and TX1 on the card that was in the thing. Anyway, you can connect a hardware MIDI device through that circuit I showed you to any hardware serial pins on your controller. So on a typical Arduino, they only have 2 hardware serial pins, and it uses them for programming, which makes it very hard to use MIDI and program the chip at the same time. On Teensy's and the ARM-based Arduinos like a Duomilanova, they've got 4 or 5 serial sets on every chip, so you can connect many hardware MIDI devices while still being able to communicate and program over USB serial.
Quick question. It looks like there's multiple uses that you can use some of those pins for.
Uh-huh.
How do you choose between what use that you want to use them for?
Basically, I would look at the card and just kind of plan out my whole project. So if I need a digital pin, I like to start with pins that are only digital pins and don't have extra peripheral features, or have peripheral features I'm not using. For instance, I haven't needed SPI for any of these projects, so if a digital pin is also shared with an SPI pin, I can use that for any digital input without impacting my project. If I know I need a serial MIDI device, I'll reserve, say, pins 0 and 1, which is what I use in this case, as the serial device, and then start using other pins for buttons, which is why I use pins 2, 3, and 4 for the buttons in my button example, is because I had already used the serial pins for this example that I hadn't gotten to yet.
Okay, cool. And then you declare what you're using it for in code, like saying, hey, use this as
Yeah.
serial button.
So when you define the MIDI instance, which is this line here, so there's a MIDI.h library that's on the Teensy site. I should actually probably take a second and, where am I? That's mouse, USB, keyboard. Oh. Okay, so if you look under the code library, there is the USB MIDI. No, there isn't. Oh well. Okay, so it's under Teensy Duino. They have the USB MIDI, and that's the one that only works over the USB serial device. For the hardware MIDI, there's another library down here under libraries called MIDI.h, which shows up there. And it has a separate page. So keep in mind there are two different types of MIDI the Teensy can do. You can use the MIDI to output MIDI. You can use the Teensy to output MIDI to any device, or you can use the hardware MIDI to send and read from any MIDI device over a hardware serial port. If you look here, there's a handy chart on their website which shows which pins each serial corresponds to for the board you're using. So in our case, we have a Teensy LC, and I'm using pins 0 and 1. If you're using a Teensy 3, you've got the same pin out as an LC, but it has more processing power. If you're using the bigger 3.5 and 3.6, they just have a lot more pins available to you. So that gives you 3 more hardware MIDI devices you could use. All right, back to the code. So in this case, you include their MIDI library, not the USB MIDI, just MIDI. And you declare a MIDI object, which will use hardware serial tied to the serial 1 port per that table, pin 0 and 1. And its function is MIDI. I forget what that last one was. I'm going back to the library reference. Oh, you can give them unique names instead of the default MIDI. So I kept the default MIDI name. That's nice. Oh, I've disconnected that. Back to the code. Okay, so I've got an unsigned long to keep track of time. I forget why. I think I stole this sample pretty much from their website and just added a joystick output. So the setup is you say MIDI.begin, and MIDI channel omni means it will receive on all MIDI channels. For people not familiar with MIDI, the protocol allows you to send up to 16 different channels with 127 notes each. So if you set it to MIDI channel omni, it will receive any note on or off signal on any of those 16 channels. If you wanted to only receive, say, channel 10 from an eDrum kit, you would set it to 10 instead of MIDI channel omni. This serial.begin is just debug serial. They did not do my handy while loop, so if you aren't connected to serial for this demo, it may not proceed to the rest of the code. In their loop, they define some variables, and then the MIDI library has a read function. So you read from there, and you set up a switch on type. So if it reads that something has been sent over MIDI, you tell it to tell me what type of signal this was. Based on the type, so if it's a note on signal, you get information about the note and show it. And in my case, I also will press a joystick button from 0 to 32 that's a modulus of the note that was sent. Same for note off, but I will release the same joystick button, and if it gets other MIDI data that isn't a note on or note off, it'll just print me a message. And then it will also print inactivity if nothing is happening. So what I have done is connect a Guitar Hero MIDI controller to the hardware Teensy port. And while it is uploading, oh, I left this open, that would break everything. We got, nope, too far. MIDI port upload. That is not happy. It still says it's compiling, so I'm just gonna wait for it to die or fix itself. I have rambled for a very long time.
I've enjoyed your rambling.
This all went faster in my head. Okay, it said it uploaded. Despite the wall of error. Hey, yeah, there you go. So you've got, as you can see, it is currently receiving MIDI data from the guitar. Here, I'll make the text bigger. So now when I press a key, you can see it's getting on and off messages.
So with that, you can only do 6 notes though, correct?
No, with the MIDI library, if you want to send it to a keyboard, you can only send 6 key presses to the computer. With the joystick, you can send up to 32, but the way MIDI works is it's all serial. So if you press all the keys at once, it will spam the bus until all those notes have been registered.
Gotcha. Okay.
So it doesn't forget, but if you send key presses faster than the baud rate, it will just back up until you run out of memory.
How would you do something like velocity?
So when you press it, it reads the note velocity as part of the MIDI note. So the first byte of a MIDI message is the channel and type. The first 4 bits are the channel, the second 4 bits are the type. So like channel 4, note on. And then the next byte is the note value from 0 to 127. And the last byte is the velocity for a note on message.
Gotcha.
Or the payload on other ones. And some of the payloads are 2 bytes long, some are only 1. It depends on what kind of message you're sending. There's a bunch of lighting protocols as well. Yep, but yeah, so as you can see, if I press all the buttons, they all come through eventually. Yeah, MIDI's fun. I don't want to cover the whole protocol though, so I will go back to code. So this entire example, I literally just imported the nunchuck library, which detects the type on its own and outputs data. I'm showing you it's possible. I'm not even sending it to a joystick or keyboard, just letting you know that you can read Wii peripherals. That's still the encoder. That means, nope. There we go. And I will hit upload. So I'll pop back onto my screen the video. So you can see here there's a little red board, my finger will cover it in a few seconds, that is essentially 4 pins that plugs into the end of a Wii nunchuck peripheral. It's called the nunchucky. 2 of those pins are 3.3 volts and ground. The other 2 are I2C clock and data signal. So I have bought one of those boards, connected it to the I2C pins on here, shown in the card. In this case, they are pins 22 and 23. Or, oh no, sorry, 18 and 19. Either one of those would work, but okay, compiling is done. My rambling is over. Essentially, buy a nunchucky board and connect it as they say, and then it is constantly reading the value. So as you can see, when I'm moving the nunchuck around, there are 3 values that are changing. You can see them at the top as AX, AY, and AZ. Those are the accelerometers built into here. And then there's also the Joy X and Joy Y, which will move when I move the stick. And as I press buttons, you can see C and Z light up on the end there. And then I can unplug the nunchuck, and you get a bunch of angry gibberish about controller error. While I go back and plug in the Wii Classic controller, but it's still showing me nunchuck debug, which doesn't work. So you have to reset when you change controllers. I will do that by unplugging and replugging the USB port and reopening the serial monitor. Okay, now you can see I'm getting left X, left right, and right, yeah. They're labeled JXL, JXR, so I'm guessing that is the X value on the left stick and the X value on the right stick, and then JYL and JYR are the vertical values, as well as button debug codes for whenever I press various buttons on the joystick.
Are those triggers analog?
It looks like no.
It looks like they're mimicking it though.
Yeah, they send an analog signal, but it's just 255 when I push the button. And these don't have click down joysticks, so those don't show up. But yeah, in general, they already wrote the libraries. This also works with all the Guitar Hero Wii controller peripherals as well. So if you have an old Wii guitar, you can just plug it into a nunchucky and turn it into a USB guitar. Yeah, so that is all the peripheral examples I planned to go over today. I also have referenced in my presentation all of my, yeah, this is the one, all my actual controller code, which is the several controllers I brought here today. I've got a Guitar Hero controller. I have the 2DX deck. I have the Step Mania box and the analog CH joystick I mentioned earlier in the presentation. So all the code for my actual controllers is online in the GitHub repos. It's basically what I've already shown you with the various input types, but mashed together and then drowned in a bunch of lighting animation code, which I'm not even going to touch today. So that's my presentation. Any questions or?
So where's the Wicked DJ demo?
We can do that after. Oh, you weren't here for Christmas when I had this thing out, were you? Okay. Yeah, it's a fun game. It will run on my laptop. I don't think we have sound in here, though. We'll figure something out. Do you have a question, or did you just move to the front for fun? Okay. He's moved to the front so he can stop the presentation. Any other questions? We good? Okay. Goodbye, Internet.